Hello everyone and welcome to Better Geotechnical Analysis and Design with LimitState GEO, which is the first LimitState webinar for 2018. My name is Tom Pritchard. I'm Principal Engineer here at LimitState, and I'll be introducing you to our speaker shortly and also rounding up at the end. Today's webinar will demonstrate a little about how LimitState GEO can be used to improve your workflow and influence your geotechnical designs. You'll hopefully also discover a little bit about the technology behind the software and how it's applicable to a wide range of different situations. The main section of the webinar will run for about 35 to 40 minutes until about 1:10 UK time, and there should be some time at the end for questions, which you can type into the question functionality that should be present in the interface in front of you. We do attempt to answer as many questions as we can during the time available, but we can't always get around to all of them, so we apologise for that. But we will, however, follow up on any unanswered questions after the webinar has finished. If you do have any follow-up questions regarding the software, you can always get in contact with us via info@limitstate.com, and we'll be happy to answer these in detail for you. So without further delay, I'd like to introduce you to our speaker for today, who is Dr. Colin Smith, and he's the LimitState GEO Product Manager.
Okay, thank you, Tom, for that introduction. So we'll kick off just to whet your appetite with a slide showing a selection of problem types that can be solved by the LimitState GEO software. So as you can see, there's a wide range of problems. There's no restriction on what you can solve. Now we'll be looking at a number of these problem types later on in the webinar. So in terms of the specific content of today's webinar, we'll be looking at workflow with the software, how it can be used to conduct what-if type calculations, and a quick look under the hood, how it works. To this end, I'll primarily be using the software directly to illustrate the key points, but I'll make use of a few slides at the beginning and end for an introduction and summary. And as this is a short presentation, the main aim is to give you a flavor of what the software can do, and there won't be time to get into the details of all the software functionality. However, there will be time at the end for questions. So before we look at the software itself, I'll give you a little bit of background to LimitState. Our mission is to provide engineers with powerful software for ultimate limit state analysis and design, by leveraging state-of-the-art algorithms and optimization technology. This innovative approach has generated a client base covering over 30 countries worldwide, including some of those shown on the slide here. So where does our software fit? Well, LimitState focuses on tools for ULS analysis. This allows us to provide products that combine the speed, ease of use and simplicity of traditional methods with the flexibility that finite elements give you to handle any problem geometry. So we feel that kind of gives you the best of both in many problem types. The only parameters you need to run the analysis are essentially the strength of your soil, C and Phi, and its unit weight. The software can deal with other parameters as well, but those are the core ones. So that's enough introduction. Let's have a look at the software and how it can be used. So we're going to start by looking at how we can solve a relatively simple problem from start to finish. This will be an extension of an embankment using a stem wall. So we need to widen an existing embankment. We're going to use a stem wall to allow that to occur, and the widened embankment has got to take additional loading. So in order to solve that problem, a sort of classical hand analysis approach, we might use a Rankine method with a virtual back down the back of the stem wall construction and try and predict the earth pressures on that. However, that in this case is a little bit difficult due to the varied surface loads and the inclined soil interface. So just working out exactly what that earth pressure distribution is could be a little tricky. An alternative would be a Coulomb wedge analysis with a virtual back and a range of wedge angles to find the most critical wedge. But we're going to look at how to solve that with LimitState GEO. So what we can do is start with a DXF import of the initial design geometry. So what I'm going to do is jump to the software at this point and go through that process. So this is the software as it appears when you start it up. You'll see the number of buttons down the left top and windows and various sub-windows. I'll explain those as we go along. So what I'm going to do is click File, Import Geometry, and pick up our DXF file. I get some options about how to import that geometry. I'm just going to click OK, and there our geometry appears in the problem. It can come with some construction lines. I'm just going to clear those for clarity. So this is our problem. At the moment, it's just a bare geometry. So we need to add materials, boundary conditions, and loading. On the left here, you'll see what we call the Materials Explorer. This has a number of predefined materials, sort of standard clays and sands, and you can define your own materials for the problem. But these are quite good just for doing sort of scoping studies. So I'm going to add some of these materials to the problem, so I can just simply drag and drop them. So I can just click on that material, very stiff clay, and say, well, let's have a very stiff clay down here. And I'm going to use a firm clay for the rest, just for simplicity. So just, well, this isn't what the original problem specification was, just to show that. So now we've got our materials, and I'm going to make my wall out of concrete, so drag and drop that there. So we've now got all the materials in place. I need to apply a load. I'm just going to show one load application here. So on this bit of boundary, I click on that, it highlights that, and then I can add a load. So I'm going to add a variable load there of magnitude 10. So anything I click on in the window here, its properties appear on the right in the property editor, and we can change the various properties or see the properties of that. So this particular boundary can have loads allocated and also have a support type allocated. So I'm going to give it a, I've done the wrong one there, actually, a variable normal load of 10 for that. So that is now set, and I'm just going to unset that one, which shouldn't have been set. So now we've got a variable load acting on that. And having done that, I could try and solve. And the software has built in a diagnostic system. It gives you a lot of information about the problem you set up, so you can check it's what you want it to be, but it also pops out error messages. So in this case, it said, I can't solve the problem, no support has been supplied. So effectively this problem is floating in mid-air. We need to give some boundary conditions. So again, I can click on the edges of the model. If I hold the control key down, I can do multiple selections, and I change the support type from 3 to fixed. Buttons up here control how things are displayed, so this puts the geometry in the middle of the window, and I just need to add the final boundary conditions at this edge, which goes fixed. And there we have it. So if I click solve, what the software does is very rapidly determines the critical collapse mechanism for that particular problem. It can animate that and shows me that in this case my wall is going to fail by sliding and a little bit of bearing failure. And what I get is a solution here we call an adequacy factor, and this is something that we need to interpret in a particular way. If I click on the number there, it tells me how that's interpreted. So what it says is that this load up here, basically, to get collapse, I have to multiply that by 17.5. So its current value is 10. I need to multiply it by 17.5 to get 175. Once it gets to that magnitude, this system will collapse. So I've got a very large margin of safety on the load there. And I can ask the software to give me a margin of safety on loads or on material properties. And we'll look at the material properties a little later in the webinar. So that's the sort of how we'd set up the model. I haven't put the actual original problem parameters in that one because it would take a little long, but I will open up a pre-existing file, this one, and that's the kind of geometry as was specified. So again, if I click on various properties, we can see that they were. So this is the fill that was going to be added to the embankment. I click on that block, it shows me the properties here. Key one here is the material, the granular fill, and it has a strength of 34 degrees, unit weight of 18, which we specified earlier. The existing embankment has properties 27 degree lower friction angle and a unit weight of 18. And we could click on other materials there to see how they are. And again, the loading up here, this central loading, if I click on that, the loading is 45 as was specified in the problem. In particular, what I want to point out is that we can also define interface properties, so the base of the wall here interfacing with the soil below. The material is something of predefined granular fill wall interface, and it basically sets the properties to be 0.75 or 3/4 of its parent material, and the parent material is the granular fill material, i.e. the material that's sat underneath the wall. So if I change the properties of that material, this interface will automatically follow those changes. Okay, so having defined that, we can solve the problem. So again, software rapidly identifies the solution. It's a finding of a few wedges, and we can animate that, see what happens. If I click on the solution again, that pops up and it simply tells me in order to get failure, I have to multiply the variable loads that are applied on the surface by 0.77 to get collapse. So basically, the system's already at collapse, and I have to reduce the loading in order to get to a point of collapse. So it's already unstable as it is. Now you'll see this window pops up characteristic value, design value. So if we're running with partial factors, for example, using the Eurocode, then in this case we're running with design approach 1 combination 2. You can see the characteristic value has been multiplied by 1.3 for this unfavorable variable load that's been applied. So that is pre-computed by the software before it does the analysis. So according to this, it doesn't comply with the code because the loads are too large as it stands. So we can have a look at the problem and see what might actually help. So one of the things we can see is when we animate it, this wedge of sword is sliding down this boundary, and this is the boundary on the weaker material. So clearly that's having an influence. So we could, for example, have excavated that weaker material a bit more before construction, and if I run the analysis, you can see the mechanism now only uses a small part of the weaker material, and this adequacy factor has gone up. So now, as long as we're above 1, effectively we've complied with the code if we've applied the partial factors. So here, that modification has actually been beneficial, and that design would comply. What I'll do is now click undo here, and we'll take back that thing and look at other ways of adjusting the properties of the problem. So one of the other things we can see if we run the original analysis is we've got failure down here. So what if we replace that with a stronger material? So if I take this basal deposit, now this basal deposit has a much larger angle of friction. If I put that down here and replace, I also need to swap the interface material. I've predefined one here called the basal deposit wall interface material. Again, it's got 3/4 of the strength of the parent material, which is now the basal deposit. I can drag that and drop that on the interface, and I've got a revised solution, so I can try that, and in this case I get a solution which is just pure sliding along that interface, and we get an adequacy factor of 1.282, showing that that does comply with the code. So that's one way we could deal with that. Again, if I revert those back to where they were, another possibility is that if we increase the surcharge on this side of the wall, we can suppress the failure underneath there by increasing the stress levels. So I've put a very small wedge of soil in there. If I just move this up to about there, that's going to increase the weight at that level. And if I analyse that problem again, I've suppressed the failure down here by having this weight there. And again, I've got an adequacy factor of above 1. So that one also complies. So hopefully what this shows you is that we can explore the problem very easily, play around with geometries, play around with material properties, and see what the problem is sensitive to, what we might be able to do with the design to actually get a viable result. Just before we leave this problem, we could look at one of the scenarios. So scenario, what happens if this situation gets flooded? So we can put in water pressures in various ways in the software. I'll just show you the simplest way, which is to put on a water table. So I can draw a water table in like that. I just need to enable the water table here. So I'm just going to do that in the property editor. We've now got that in there, and I can click solve, and it will tell me how stable the situation is. Now you can see in this case, in this flooding scenario, the adequacy's gone down below 1, so this would not comply if that flooding was a likely instance in that case. Once I've done my analysis, if I want to report, I can click Analysis Report here. I've got various options about what to put in, so you can have whatever information you wish, and it produces a report in a RTF format, so that can be imported into a Word document, and it gives you a summary of the project, the mechanism of failure, the adequacy factor, loading types, and various bits of information about the boundary conditions, the materials used in the problem, etc. So that is available to when you've got the final design sorted out. So that's a quick look at exploring different scenarios. If we just jump back to the PowerPoint, close that down. We can also do what-if type analysis. So we'll look at a slope stability example in this case. So the problem we're going to look at is fairly simple: slope 10 meters high, 20 meters long, with strength parameters 5, C' to 5, phi' to 30, unit weight of 20. If we're going to analyze that by sort of conventional method of slices method, that type of analysis requires some kind of assumption of in-slice forces to be chosen, and often you've got to specify zones of entry, exit points, and centers of rotation. With the LimitState GEO software, you don't need any of that. It just finds a critical mechanism directly. So, oops, sorry, I just jumped ahead. We'll look at that in the software. So just open up the file which I've prepared for that one. Okay, so that's the same slope problem. The material we have here, if I click on the material there, it's soil A, so that's that material, C' to 5, phi 30, unit weight of 20. Now what we're going to do here is a factor of strength analysis. So rather than asking the software what size of load is required to cause failure, we're going to say how much do we have to factor the strength down to cause failure. So if I click solve on that, it runs through a range of failure mechanisms and determines that we have to reduce the strength by 1.63. So if I click on here, it tells me what it's done. It's taken the C' and phi' properties of soil A, shows me what the characteristic value is, and they have to be factored down by 1.6 to these values to actually get collapse. So that 1.63 is very close to the method of slices result, which was 1.6. And generally, they come out very close. We've got the flexibility in this to do what if. So what if somebody puts a surface load on up above at the top of the slope? So I'll put a variable load of 5 up there. And again, run the analysis, see how that affects things. In this particular case, it doesn't change things much. It's taken the adequacy factor down to 1.62, hardly any difference. And looking at the mechanism, you can see that that surface load for this particular mechanism is only having a minor effect at the top. It's not the whole load that acts in that particular case. We can also use the software to look at, for example, pre-existing slip surfaces. So if I just take that surface load off, I'll add in a very simple pre-existing surface. So I can just use the line drawing tool to draw a line in to change the geometry here. So that's a linear pre-existing surface. Well, let us assume that because that has undergone pre-existing slip, it's going to have a lower strength. So in this particular case, I'm going to just allocate it for simplicity the property of a soft clay. So just drag and drop. So that line now has that property. Perhaps it wasn't originally straight, maybe it was curved. I could add in extra points to add in a curve. I'll just add in 1 to give it a slight curve in that case. So again, if I run the solution, it rapidly identifies the critical mechanism. And this time the critical mechanism clearly is taking advantage of the pre-existing slip surface and using that to slide down, because that's obviously going to be weaker. So we get a different mechanism sliding down here, and our adequacy factor has dropped to 1.2. So we're now a lot less than the original 1.6. So software is again, we'll just find the critical mechanism and we'll seek out those aspects in terms of slope stability or weak layers of material. And if I click on this factor here, you can see that it said we've got to divide the strength of both the soft clay and the soil by those properties to give me that result. Okay, so that's a quick look at slopes. We'll just wrap up in terms of the examples, looking at some foundation problems. So I'm going to open up this problem here. Okay, so here we've got a foundation. This is really to illustrate the use of partial factor sets. So what we've got here is a very simple surface footing. We've applied a load here, which is a permanent load of a half. Now the foundation has a width of 1. Whenever I click on here, its properties appear here, but its geometry appears down here. So the geometry of that line runs from -1 to +1 in the x direction, so it's too wide. I multiply by a stress of a half, I effectively get a unit load. So I've set the software up in this case to give me a result which tells me what magnitude of load on the foundation would actually cause collapse simply by applying a unit load to the top of the foundation. We've got a soil underneath that, which has these properties. It's actually set up to be undrained with an undrained strength of 70. All materials that we define the properties for, we can define effective stress parameters, C' and Phi' and undrained parameters, and we can make the material behave either always drained, so always using the effective stress parameters, or undrained, always using the undrained parameters, or drained, undrained, and that allows us to set a global switch in the software, which is set by this property editor here, which is this long and short-term analysis. So if I set long-term analysis to false, it's going to do a short-term analysis, so it will use the undrained strength where it has a choice. So effectively this material is going to have the undrained strength of 70. We've got a surcharge either side of the foundation, and that has been set as a permanent load of 10 kPa, and we've defined it to be favorable. So we need to set these properties to be favorable or unfavorable if we're going to be applying Eurocode factors, which is how this problem is set up. And if we look at those particular factors, if I go Analysis Scenario Manager, what we have in the software is what we call a Scenario Manager, which allows you to run the analysis several times with different partial factor sets. So here we're going to run it once with unit factors applied, then we're going to run it again with Eurocode 7 Design Approach 1 Combination 1 factors applied, which effectively are factoring up the unfavorable loads, and then again with Eurocode 7 Design Approach 1 Combination 2 factors, which are essentially factoring down the material strengths here. So we're going to get 3 different analyses, and if I click Solve, those will run through. So you can see the different results we get there. So the critical one is Design Approach 1 Combination 2 as you'd expect. And this is essentially saying that we've got to apply a load of 502 to that foundation, 502 kilonewtons, because we set the actual stress there to be unity to get collapse. So that's basically its load capacity. Now we've looked at a surface footing here. We can look at different geometries. So here we'll just look at a footing that's partially buried. And again, we've got the same sort of loading and material. So I click Solve. We get a slightly different mechanism, slightly higher load capacities. And in this case, again, the critical case is Design Approach 1 Combination 2. Now we can also look at what would happen supposing that foundation has to take a lateral load. So currently it's got a normal load of 1/2. I'm going to add in a little lateral load or a shear load to the surface of that 0.2. So now it's an inclined load. How does that affect the solution? So I click Solve. The mechanism changes. It sweeps to the right now. If I animate that, see it moving to the right. And the adequacy factor and load capacity is dropped to 390 from around 500, so it's a much more significant change. And you also see that the software has popped up a note here. It's saying the loading on B5 is now not favorable, but you've specified it as that situation. So if I click on that, that load is highlighted. It's saying this is now no longer favorable, and it isn't. If we look at the mechanism, that load is actually assisting the failure by pushing down on this side. It's still favorable on this side because it's being pushed up. So again, the software will give you that little check. So if your initial assumptions aren't correct, it flags that up and you can change the setting as you go. Okay, so that I hope has given you a flavor of how you can do kind of what-if type analyses. What if I change the loading on my foundation, or what if I get a pre-existing slip surface in a slope? We'll now jump back to the presentation to wrap up. So you've seen how we can use the software. What I haven't explained is how the software works, what it does, so we'll just quickly run through that. So the underlying technology that it uses is a method called discontinuity layout optimization, and that can be used to provide rigorous upper bound plasticity solutions. It was developed back in 2007, published in the Proceedings of the Royal Society, and that was the outcome of an EPSRC funded research project carried out at the University of Sheffield. And while there's a lot more to it than this, I can explain the core principles in 4 diagrams. So here we have our problem domain. We have a block of soil, so a fixed boundary to the base and to the left, and a load on the surface. To solve the problem, I don't discretize it into elements as I would in a finite element software, and we actually populate the domain with nodes. So here I've got 4 by 3, 12 nodes in the problem. And what we do is we connect every node to every other node to form potential slip lines. So if I've got 12 lines there, I get 12 times 11 over 2, 66 possible slip lines. And essentially what the software does is it uses linear optimization to pick out of those the mechanism that gives us the critical collapse mode, which ends up being this one. So we've just got 6 of those original 66 slip lines, form the critical collapse mode, and we can then show what the mechanism is in that particular case. Now, the accuracy of the solution does depend on the number of nodes. Here we're only solving with 12. Typically you'll be solving with maybe 1,000 nodes, and therefore of the order of 1 million potential slip lines. And obviously the more nodes you use, the higher the accuracy, just the same way as fine elements. The finer the elements, generally the higher the accuracy. So here you can see a gravity wall problem being solved. You see the nodes in the background, and then the software putting together those slip lines that form the critical mechanism. Once it's identified those slip lines, it is then able to put them together as blocks and animate those to help interpretation of what's going on in the problem. We've applied this to many, many benchmark problems. So for the classical pyramidal punch or footing on a clay soil problem, you get within 1% of the exact known solution in under a second, and you can see that classic fan zone solution in this case. One of the advantages of this method is that it can handle mathematical singularities without any difficulty. What you often find in collapse mechanisms is that you get a lot of these slip lines meeting at a point, and that gives you a mathematical singularity, which can be hard to deal with using finite elements. But with this method, it's just dealt with inherent. There's no extra programming or anything. It's just taken care of by the standard method. The method has been verified against a wide range of closed-form solutions and benchmarks from the literature. We've put over 100 results on the website, so you can find the relevant page. Gives you a whole load of examples. This one that we've put here is for an anchor in clay soil, effectively, at a burial depth of 10 times the anchor width. The benchmark solution in the literature was 17.97. The solution from the software with using not that many nodes is 18.1, so a discrepancy of less than 1%. There are a wide range of other problems, slopes, foundation problems, etc., retaining walls, that you can look on the website. And every time the software is modified, we automatically run thousands of tests to make sure that it's generating the results that we expect. Software has also been used in quite a wide range of academic publications. So again, you can download this bibliography, which we've listed by type: foundations, slopes, retaining walls, reinforced soil, etc. So you can look through those and see where that has been used for the in academic work. So we're coming towards the end of the presentation. Just going to wrap up with a few application examples, just again to remind you the breadth of problems that we can solve with the software. Gabion walls, working platforms, trenches next to a footing, anchored sheet pile walls. So we have materials or objects in the software from which you can effectively define sheet pile walls or soil reinforcement or anchor tendons, and those can be modelled. And in the case of sheet pile walls, the software will model bending failure of the wall itself, and a range of other problems such as key wall, slope construction, offshore problems, all been used. Software has been used to solve all that full range of problems. So just to wrap up, hopefully what I've shown in this short webinar is that in terms of workflow, it's straightforward from geometry import to reporting. It's what we hope is an intuitive user interface, so you're in control of the problem. Generally you solve with one mouse click. It's easy to handle partial factors. So a lot of customers use the software interactively to answer what if, because you get those answers back very quickly, so you can explore geometry, material, property type changes and just get a feel for what is affecting this problem and the best way to solve it. And hopefully you've seen that it's the same software solves any ULS problem type, so there's no need to impose idealization or correction factors for non-standard geometries to try and get your solution to work for a slightly different problem. No need to learn how to use many different programs. It can solve the full range of ultimate limit state problem types. So at this point, this brings us to the end of the presentation, so thank you for listening, and we've got some time to answer a few questions. Okay, so I've got a few questions come through already. So one is each problem type a different module? Because I said the method is general. So essentially, the software is very general. You can draw any geometry and solve it. The software does come with a wizard which allows you to create a range of different problems, but these are all essentially general, all parts of the same software. These aren't separate modules. All these wizards do, for example, the stem wall wizard, is allow you to define some geometry, rapidly build the geometry of the problem and the materials, but once we get to that stage, the software is fully general. It will solve that problem. And you can easily change the geometry of the problem or convert it if you wanted. So just by moving things around, I can change this rather weird geometry. I could add a foundation in there. It's just solving a collapse problem using this general purpose method, discontinuity layout optimization. So there's no restriction on the geometry that it can solve. I've got a question saying, can we model soil reinforcement? So if we look back at this list of wizards, we do actually have one that's a reinforced soil wall. So this is setting up a geometry where we've basically got facing panels with a reinforcing layer behind it. So if I click on that reinforcing layer, reinforcing layers are modeled with what we call engineering elements in the software. And depending on whether you're modeling a soil nail or a strip of reinforcement or a sort of planar geotextile type reinforcement, you can set various parameters here, pull-out factors, moment of resistance, tensile strengths, compression strengths, to define how that material behaves. I haven't got time to go into the detail of how all that is done and how to represent different material properties, but essentially that is modeling a reinforcement element in the soil. Following the same kind of mechanics that is followed in conventional calculation methods, but in this particular case, it's fully general, so it can work with mechanisms that overlap the reinforcement and take care of the interactions as appropriate. Okay, I've got a question here. How can I choose the loads, their extension position to apply the adequacy? So if we look at this problem here, I've got a load applied up on this boundary. Basically, I'm free to apply a load to any boundary I like. So this current load here it's a variable load of 5. If I wanted a load behind here that was different, I could, for example, apply a variable load of 12 to that. And if I didn't want the load fully across the top of that wall, I can split the boundary up. So I can add what's called a vertex here. Just click on that. I can add a vertex. That's now split this boundary into 2 parts. And if I didn't want to load, for example, at that front part, I can just set a 0 there. So anything I could do to the boundary, and if I wanted the boundary to be slightly inclined or so on, I can grab the point, move it up. So I've got full flexibility on where I can put the loads, and they can go on any boundary essentially, and what their magnitude is, and whether they're going to be permanent variable or accidental according if we're going to use Eurocode partial factors. So I solve that, I should get a different problem solution because I've got some surcharge behind in that case. Got a question, does the software calculate deflections? The answer to that is no. It's ultimate limit state software, so it is designed to calculate the ultimate limit state or collapse state, so it's looking essentially for loadings that give collapse. And that's part of the reason why it's so easy to use and is so flexible. It's not calculating deflections in there. We are dealing with strength parameters. So it's a ULS design software. Got a question, can we analyze axisymmetric problems? So the software as it stands is currently plane strain only. So if you wanted to model a circular foundation or a square foundation, you can still use the software to explore what would happen if you had layers under that and how that might affect things, but you'd have to adopt your own sort of shape factors to adjust the results to that particular scenario. Okay, got a question about rigid inclusions. So let me just pick another geometry. Let's go for a gravity wall. I'm not quite sure exactly what's being asked there, but if I've got a lot of fill behind the wall, but I know there's a rigid inclusion in there, I'll just show you very generally. I can click on this tool here, which is polygon tool, and draw whatever shape I wanted. That then puts that there. If I want that to be rigid, or say made of concrete, I can just put a concrete lump in there, and then run the analysis, and the failure mode will go around that. So basically, no, in this case it's locked up for some reason. So it's saying that probably the way I've set the nodes up in this particular problem has locked it up. So what we generally recommend in this type of analysis is that for speed, when you're exploring the problem, we use a relatively low number of nodes, and that is defined by this quantity here. And then when you've got the design to where you want it to be, you then move to a very fine number of nodes. That puts more nodes in and gives you that higher accuracy in that case. All right, probably one last question. How can I calculate against retaining walls, sliding, overturning, and bearing? So if I just go back to that one. So if we analyze that problem, in this particular case, the failure mode is sliding. That one is sliding along there. It's not overturning. It's not undergoing bearing failure. Now, conventional calculations often ask you to check against sliding, overturning, and bearing as 3 possible failure modes out of effectively an infinite number, because you could get a combination of sliding, overturning, or overturning and bearing, and so on. So for hand calculations, you can't be expected to calculate all the different combinations. So you're normally asked to calculate sliding, overturning, and bearing separately. And if those pass, then it's assumed that any intermediate mechanism is then also passed. The software isn't really looking at sliding, overturning, and bearing. It's just looking at the most critical failure mode. So in effect, it's automatically considering all those possible failure modes during the analysis, and the one that it comes up with is the most critical. So in this case, sliding is most critical, and it's more critical than an overturning failure or a bearing failure. You don't tend to get those on their own, if I made the soil at the base of this wall extremely weak, so I'm going to put a very soft clay down here, you might say, well, the wall will just fail by bearing. Depends how I've set the problem up. I'm actually asking the software, what do I have to do to the weight of material down here? So what I actually end up with in this particular analysis is I'm getting effectively sliding and bearing failure, and I'm getting a kind of clay extrusion problem down at the base there. But again, it is finding the most critical mode, and it's not necessary to consider each one separately. Okay, well, I think that brings us to we've run out of time at this point, so I'm just going to hand back to my colleague Tom to wrap up. So thank you very much for listening, and I hope you found that useful.
Thanks, Colin, and thanks to everybody for joining us today. Like Colin said, we do hope you found the webinar informative, and for people who aren't actually current users of LimitState GEO, we are going to get in touch over the next few days just to find out if you have any further questions about the software and see whether you think LimitState GEO might be useful for you. As mentioned at the beginning, if you have any follow-up questions outside of this, then please do email us on info@limitState.com and we will get back to you. You may also be interested to know that we have a number of forthcoming webinars throughout the year that will cover all the LimitState product range, and some of these will focus more on particular problem types and applications. So if you are particularly interested in, say, slopes, then there should be a webinar to deal with that for you. Yeah, please look out for the event notifications that we'll send out via email, and we'll also post on our website at limitState.com/events and also on LinkedIn. With this particular webinar in mind, we'll be sending out a link to view it again on our YouTube channel this afternoon at some point. So finally, again, just thank you all for taking the time to join us today, and we hope to see you again for one of the future sessions. Goodbye.